Okay. So the basic idea here is to gather evidence for a particular way to interpret quantum mechanics. And as you see there, it's called the objective indefiniteness or literal interpretation of quantum mechanics. And that name was given to it by Admiral Shimoni, who is a PhD in physics under Wigner, and but also had a PhD in philosophy. And so the basic idea is we don't have an intuitive idea of what objective indefiniteness is. So the idea is, let's just look at the math. And the mathematics at the most elementary level to represent indefiniteness and definiteness is the partitions on a set. And so we start there, and then we lift the mathematics of partitions on sets to vector spaces, and then we specialize to Hilbert spaces, and we see that we get the way it fits the mathematics of quantum mechanics. So that's the sort of evidence for this view that the way to interpret that math is in terms of objective indefiniteness. So that's the strategy for the talk. And here is Shimoni saying the two basic ideas, indefiniteness and superposition, clearly conflict with common sense. And when he says it's the literal interpretation, he says, well, that means that the quantum state is a complete description. It's not just an epistemologically incomplete description, but it's a complete description, which nevertheless has indefinite values until you perform a measurement, and then the value may become more definite. And that this conflicts with common sense in very fundamental ways. So this is what he called the literal interpretation of quantum mechanics, and taking the formalism literally as giving representation of objective indefiniteness, not just subjective indefiniteness of human knowledge. And you have a number of other physicists and philosophers of physics that have made similar things. That Steven Weinberg, for example, says a particle can be neither definitely here nor there, or spinning neither definitely clockwise nor counterclockwise. And the important thing to notice about that careful description is it's very unlike the pop science description of a superposition as being in both states at once, which is absurd. And Weinberg is very careful, says not definitely here, not definitely there. So it's an indefinite state between here and there, not something that's both definitely here and there. And similarly for the spin. And you've got a few other philosophers, Feyerabend, inherent indefiniteness is a universal objective property. Peter Mittelstadt, quantum states are unsharp or incompletely determined. And so I called attention here to Weinberg's careful statements, which I'm going to criticize more later. But superposition should not be interpreted as definitely being here and there, or the cat being definitely alive and dead, but as something intermediate that's neither definitely one nor the other, and would be sharpened into one or the other definite state by measurement. So we shouldn't try to make sense out of something being simultaneously in two definite states, which is absurd. But what does it mean to be in a superposition that's objectively indefinite between two distinct states? And that's where the whole mathematics around partitions is going to come in. So our common sense view is that reality is definite all the way down, and so that you can ultimately differentiate any two things by just digging deep enough into their properties. And so that's the way we sort of automatically think reality is. And the notion of objective indefiniteness says no, that there is you get down to a certain level and it's objectively indefinite between the two. And there's no such thing as digging further into the properties to find that how one thing is different from another, how two electrons are different or two protons, and so forth. So where's the math that conceptualizes this notion of indefiniteness? And so that's where we get into now partitions. So you all know what a partition is. You have a universe set, and a partition is a set of subsets. And I'll keep it finite for the talk because we're only interested in conceptual issues, not mathematical generality. And the blocks are disjoint and their union is all of U. So they partition you into these different blocks, also called cells in some places. So given a partition, what it says is that the elements within a block are indefinite to each other, indistinct from each other, whereas the elements of U that are in different blocks are distinct from each other. So the partition makes them distinct. Partition does not differentiate between the elements inside a block. So you've got to do refinements of the partition to make the blocks smaller and smaller if you want to differentiate the elements inside a block, to make them the block less indefinite, more definite. And so just to start trying to connect our intuitions or quantum mechanics notions to partitions, think of a block as a superposition. So it's a superposition of all the elements inside that block, and it's distinct from the other blocks. So the other blocks, as it were, are disjoint or orthogonal, as we'll see in the vector space case, as they are in a partition. So the basic operation, there's a full set of logical operations you can perform on partitions, but the only one we're going to need is the most basic one, is taking the join of partitions. And I warn you that in some books, they write the lattice of partitions upside down, as it were, and so they call it the meet. So the idea is the join, same idea, no matter which way you write the lattice. It's the partition whose blocks are all the non-empty intersections. So you got the blocks in pi, the blocks in sigma, and none of the blocks in pi can intersect each other, none of the blocks in sigma, but they can intersect each other. And so you have a new partition. So every point has to be in two blocks of pi and sigma. So every point will be included here. And these intersections are obviously disjoint. So that's the join, is that new partition, which is in general more refined than either pi or sigma. So we're going to just take those notions from partitions and then lift them up to vector spaces through this process of linearization. And then particularly we're going to go to Hilbert spaces for the final interpretation of quantum mechanics. So that's the strategy of the talk. This is how following the math will lead to an objective indefiniteness or literal interpretation of quantum mechanics. And here is a sort of picture you might keep in mind, very simple, but you have the lattice of subsets, which is Boolean logic, and you have the lattice of partitions, which is partition logic. Here, the relationship is just inclusion, and here the relationship is refinement. And so if you think in terms of the old Greek concepts of substance and form, then this, and think of this as a creation story going from the bottom to the top. This creation story starts with nothing, and then you start getting elements being created. So you start with zero substance, and then elements are created. And in physics terms, you think of substance as being energy. And then more and more are created until you get your universe, full universe, which just has three elements here. So all the elements are fully formed when they're created. There's no increasing specifications to what the element is. So the creation, there's fully formed, and then there's creation of substance. But when you go over to the partition lattice, it's just the opposite. all the substance, all the energy is there in the beginning, but it's totally undifferentiated. It's all in the same block, A, B, and C. And so then you have, as it were, breaking of symmetries to form more refined partitions. So in this partition here, for example, B is differentiated from A and C, but A is not differentiated from C. And similarly for all the others. And then finally, you reach the top, which is everything is a singleton and is fully differentiated from the others. And so substance is increasingly informed by making distinctions. And this, of course, ties in with the notion of information is basically counting distinctions. And so this fits in with the story about information, but that's not the story today. So we have two creation stories. One start here. In the beginning was the void, no substance, and then fully definite element. Its, we should say, are created until a full universe is there. But the quantum version, in other words, the partition version, in the beginning was the blob. Everything was blobbed together. All the substance was there. All the energy existed, but the energy had no, it was all in what Weinberg's book about the Big Bang is called perfect symmetry. So it's all perfectly symmetrical, no distinctions. In other words, the what is called the indiscrete partition or the blob. And then symmetries started being broken. And that was in the Big Bang, which created distinctions or dits, and symmetries are broken. The substance was increasingly informed to reach the universe U here with fully distinct elements. So these are the two possible creation stories based on these two dual forms of logic, subset logic and partition logic. And you see that the partition version actually at a super elementary level actually reflects the current cosmology of the Big Bang, where all the energy was conserved, but it wasn't differentiated, and then was differentiated by symmetries being broken. So that's just sort of a beginning way to think about these concepts, and particularly here where you see things become more and more differentiated as you move up. So not differentiate here, and then each partition is a different way to differentiate things until you get to the fully differentiated partition at the top called the discrete partition. That's everything is a singleton. The indiscrete partition is where everything's blobbed together at the bottom. So that's where we start. Now we move to vector spaces. And so this is by this process, I think would be called semi-algorithmic. And you start with a set concept, such as the set concepts we just talked about with partitions, and you generate the corresponding vector space concepts. So the yoga, here is the way the yoga works. You start with the basis set of a vector space, and then you apply the set concept to the basis set, you see whatever it generates. So the basis set is like the vector space version of a set. You apply the set concept to it and see what generates then in the vector space, and that gives you the corresponding notion. So the universe U, what is generated from the universe U, if you take the universe to be a basis set, is obviously the whole space. Cardinality of the set U, what is generated is the notion of dimension of the space. So cardinality and dimension are corresponding concepts at the set level and vector space level. And subset generates a subspace. And you take the subset of a basis set. So subset and subspace. So those are sort of elementary correlations between the two concepts. Then we go bring in a little more machinery at the set level. We start with the numerical attribute. So an attribute would be something going to 0 and 1. But here we talk about a numerical attribute going to the underlying field of the vector space. So here's your set concept as this numerical attribute, just assigning elements in the field, some given field, to the elements of U. And that defines a operator on the space. And here's the definition of the operator, that the F applied to any u. Remember, small u is an element of a basis set, is f of u times u. And so you define the operator in a basis set, you extend it linearly to the rest of the space. So you have a definition of a linear operator. So linear operator is really just a numerical attribute re-expressed in vector space terms. And here is a little thing where I said, okay, start with your numerical attribute, and suppose you say, well, that the function f restricted to some subset S is just k assigned to each element of S. So think of that as like a little equation. What subsets S and what elements of the field K satisfy that equation? When f is restricted to that, it just assigns k to each thing. So these are just the constant sets, obviously. And the vector space version is the eigenvalue and eigenvector equation that f applied to u is this. So the corresponding thing to an eigenvector, namely a u that satisfies this, is a subset over here on which f is constant. So constant set of a numerical attribute corresponds to an eigenvector, and that value on the constant set is obviously corresponds to the eigenvalue. And then, as you know from your linear algebra, you can express a linear operator in terms of this sum of all the eigenvalues times the projection down to the eigenspace. And here's exactly the same thing for the f itself. You go over all the k in f of u, in other words, all the elements of k that are in the image, and you multiply k times the characteristic function for f inverse k. So f inverse k is the biggest constant set that's constant with value k, and so that's 1 there and 0 elsewhere, and so f is just k times that 1 if the element of u is in that set and is 0 if not. So that's just a way, that's a what would be called a spectral decomposition of f, and here's a spectral decomposition of the operator f, capital F. Then you take, on the set side, you take the set of all constant sets, which is the power set of f inverse k, and that corresponds to the eigenspace, which is all the k eigenvectors that have, so every subset that's constant on small k corresponds here to the eigenspace of all eigenvectors that are constant on the element k. Then you suppose you have another numerical attribute defined on the same set u, and this is going to be important. Keep track of whether it's defined on the same set or another set. It defines another operator by the same formula. And so when you have f and g defined on the same set, that corresponds to f and g having a basis u of simultaneous eigenvectors. So simultaneous eigenvectors are going to be corresponding to numerical attributes defined on the same set. So that's using our yoga of linearization a little bit. And then we say, well, our fundamental notion is partition. So what's a partition of a vector space? So we apply a set partition to the basis set, and you see what it generates. So if you have a set partition of a basis set, then each block will generate a subspace, and the set of those subspaces will form a direct sum decomposition. So that's the vector space notion of a partition, is a direct sum decomposition of the space. And if your set partition was the inverse image of a numerical attribute, then this is your partition, and each subspace then each subset generates a subspace, which is the eigenspace of that operator you define with small f, and so forth. So the whole vector space is just the direct sum of these eigenspaces. So that's down here. Now notice a direct sum decomposition is not a set partition of the vector space. There are lots of vectors that are not in any of the eigenspaces. I mean, you know, superposition vectors all over the place, which are not in them. But the property that defines a direct sum decompositions, every vector can be represented uniquely in just one way as a sum of vectors from the eigenspaces. So then we say, okay, if this is such a great correspondence, let's work backwards. Can we define a set partition as a bunch of blocks that act the same way so that every subset is uniquely represented by the projections down to the eigenspaces? So here we go. So we say it's usually defined as a bunch of blocks of disjoint, joint, exhaustive. But can each subset be uniquely expressed as the projection? This is a projection operator on sets as the union. In other words, like the sum here, the union of the projections down to the BK, and that's true, and that's an if and only if. So that you could have defined set partitions in that way all along, and would have got the same notion. So that's really a solid connection then between partitions and direct sum decompositions, that each one can be defined in terms of the other in that sense. And the last notion we need to lift up here to vector spaces is the Cartesian product of two sets. And so we assume we have two different basis sets, U is basis for V, U prime basis for W. And the product of the basis sets is this. And what do they generate when we linearly extend these ordered pairs to a whole space? And that turns out to be just the tensor product, not the direct product of vector spaces, but the tensor product. And you represent the ordered pairs here as this sort of a tensor thing, and then you linearly extend it to the whole. But they generate linearly, and that object they generate is the tensor product. So direct product, the linearization of it is a tensor product, and the element of the direct product linearizes to this basis element of the tensor product, because these are the basis elements in the tensor product. So that's developing the yoga. So now we want to just summarize a bit that we had those two logics, the logic of subsets and the categorically dual to subsets or subobjects is quotient objects or partitions or equivalence relations. And you have the two different logics. Boolean logic of subsets goes back to Boole. Logic of partitions goes back to 2010 or so. And then we have apply the yoga to subsets would give us a logic of subspaces, and applying the yoga to partitions would give us a logic of direct sum decompositions. So the logic of subspaces is what is now called quantum logic, originated from Birkhoff and von Neumann in 1936. And so that means there should also be a quantum logic of direct sum decompositions, and that was published here in 2018. So that fills out the picture on both sides using this connection between subsets, subspaces, partitions, and direct sum decompositions. And then if you go to the quantitative versions, what's the quantitative version of a subset? Well, that's, and this is a sort of a analogy that Jean Collarota always pointed out in his, both in his, some of his books and also in his lectures at MIT on combinatorics. The probability is the subsets as information is to partitions. And Rota didn't quite have it figured out exactly how a partition should be quantified, but we know how it should be quantified now because we know that its are dual to dits, its and dits, elements of a subset or distinctions of a partition. So the probability that was developed by Boole was just the normalized number of elements in the subset, or you could think of it as a projection, the cardinality of the subset you get by projecting down from the whole of U to S. And that was developed by Boole. You see the name of Boole's book. Here was even Mathematical Theories of Logic and Probabilities. And so then you do the corresponding thing for partitions. Partitions are made up of distinctions. And so the logical version of information is the cardinality of the set of distinctions of a partition normalized, since these are ordered pairs now, distinction members, an ordered pair of elements in two different blocks of the partition. And that's you could also think of it as applying the product probability distribution, if your points have probabilities attached to them, to this subset here of U cross U. And the interpretation is, if you do two draws, independent draws from U, what's the probability of getting a distinction of pi? That's how you interpret this thing here. And that was published in 2009, Counting Distinctions. So when we then apply the quantum, just as we had the quantum versions of partitions or subsets and subspaces and partitions and directs, let's now do the same quantitatively. So when you start with the notion of probability and you move to the quantum version of probability, it's equal to the trace of the projection of the state, which is now in the form of a density matrix. And that's analogous to here, the projection of U down to that subset. So here you have the projection down to a subspace times the representation of the state here, like the universe you're starting with. And that gives you the probability of a state being in the subspace U, where this is your density matrix. And so the interpretation is, if you do one measurement of U, and this is where the measurement basis would be whatever basis the density matrix is expressed in, that gives you the probability of getting the state in U. And this goes back to von Neumann's original mathematical version, translated and published in 55. And then you do the same for quantum logical entropy. So you have projection down to the subspace, in this case, not the dits, but the q-dits, which are the pairs of basis vectors that have different eigenvalues, and times so this formula here is the analogous to this. You have the probability distribution over the dits. Here you have the projection down to the dits times this probability distribution on the tensor product. The interpretation, as you would expect, is the two measurement probability of getting a q-dit, in other words, a pair of eigenvalues, different eigenspaces, namely different eigenvalues, in doing two independent measurements of the same state psi. And that's been published a number of different places. So here we have the two concepts, the logic at the logical level, the quantum version of the logic, and then the quantitative version of probability, quantitative version of information, and then the quantum version of the quantitative and the quantum version of the quantitative there. So it fills out the whole picture. So now let's go and start interpreting using this machinery we developed and interpret the major operations and mathematical notions in quantum mechanics. So it's interesting that there are two different ways to represent states in quantum mechanics, namely as vectors, state vectors, or wave functions, if you wish, in Hilbert space, and as density matrices. And it turns out, for our purposes, density matrices are really the way to go, that they are the right way, as it were, because all the off-diagonal elements in a density matrix are called coherences, and that signifies that indefinite between those elements in a partition block. So the notion of a partition block, you're saying two elements are in the same block, it's like saying those two elements here have a non-zero off-diagonal term that tells you they're cohering together in the density matrix formulation, and that's not so obvious when you just do the vector, state vector formulation. So what I'm going to do here is I'm going to, just for sake of simplicity, develop these theorems about quantum measurement, but just use real valued density matrices, since that allows us to directly connect to the classical versions. And then the quantum version is just the complex number version of exactly the same thing. So let's start back in our sets where we have a universe U, we have a probability measure on the points of view. Here are the point probabilities, two partitions, same two partitions we had before. But now, since we have point probabilities, we have a probability of each block, just the sum of the point probabilities for the elements in that block. Then we want to associate, to represent this stuff, with the density matrix. So you start off with the density matrix for each block, and that's defined like this. So the JK entry in the density matrix is this product here, if they're in the same block, and a zero otherwise. So we're already building into our density matrix the notion of coherence, that if they're in the same block, means they cohere together, and that's already incorporated here. And so the non-zero off-diagonal elements represent these coherences. And then we just take the probabilistic sum. So the density matrix associated with the whole partition is just a probabilistic sum here, and these probabilities just knock out the ones here in the denominator. So you know what the elements of this thing are going to be, just the square root of this product of the two probabilities. Then the notion of logical entropy, which you could express this way without any density matrix concern, is remember, it's the probability of getting two elements in different blocks. So you just subtract off from one the probability you got two elements in the same block, namely the sum of the probabilities, block probability squared. And then you just use now the density matrix formulation, same information, just in a density matrix form. You square the density matrix and take the trace. And that there's a theorem that these two notions are exactly the same. So we can move on from that and say if we see the dit set of a partition, the cardinality of U is n, and so it's n cross n, and you can form a projection matrix n squared times n squared, where it's going to have these four indices, is just this it's a bunch of 0 and 1s, and the 0 and 1s in this whole matrix, which is a diagonal matrix, just indicate whether these two elements are in different or the same. And here we're saying they're in the different. So when they're in different blocks, you get a 1 in this projection matrix, this diagonal projection matrix. You get a 0 if they're the same block. So then we have another formulation of the logical entropy. So first of all, I said it's the 1 minus the the block probability squared, but you can also just say of all the elements in different blocks, just take their product probabilities, because that's it's the probability that you'll get two elements in different blocks, or in other words, that are a distinction. And so that's one way to express it. And then that turns out to be equal to the trace of this projection here times this tensor product. And so the projection had to be the same dimensions as the tensor product. Each of the density matrices n by n, so the tensor product is n squared times n squared. And so that equals also this other formulations. You have a lot of different formulations of logical entropy, and all these formulas generalize immediately to the complex case where you have the qubits, in other words, pairs of basis vectors that have different eigenvalues correspond to the distinctions of the partition. So using just this simpler framework here, what is the partition analysis of measurement? So that's the big question. What is measurement? And in quantum mechanics, so let's see if we can get an analysis of measurement using this machinery of partitions re-expressed in nice vector space terms with density matrices and projections and so forth. So we start with, say, a measurement transforms a pure state, in other words, one where the trace of rho squared is 1. Every density matrix has a trace of 1. So if you square the matrix, do you still get 1? If so, it's a pure state. If not, it's a mixed state. So that's sort of the criteria you separate out mixed states from pure states. So if you start with a pure state and do a measurement, you get a mixed state. And if you start out with a mixed state, you get a more mixed state in the usual quantum thing. So let's assume that we start with a mixed state, or it could even be a pure state, but it's represented by rho of pi. If pi is the indiscrete partition, or if you have only non-zero probabilities on a certain subset, it would be the version of the blob where it's just on those subsets. So it's really the more general case. So it could be the blob. Then we perform a measurement using the numerical attribute which defines the partition sigma. So here we start with a state that's already density matrix of a partition, and then we say, okay, let's now take a numerical attribute and define another partition. So in quantum mechanics, the effective projective measurement on a density matrix is given by the Luther's mixture operation. So this is something that's been around since the 30s, I think. So this is the operation on density matrices that describes what happens in a measurement, what happens in a projective measurement of the density matrix. So here is the way it's defined, the Luther's operation. You've got your whatever the attribute or the observable in quantum mechanics. Here in our set case, it's just sigma. But in general, you're going to have a observable, a self-adjoint operator, and they'll have eigenspaces with eigenvalues lambda. P lambda is just projection down to that eigenspace. Then the measurement operation transforms rho into rho hat. And here is the way it does it. So you take the original rho that you're measuring and measuring by this operator with these eigenvalues and eigenstates, and you perform these projections, pre and post multiply by those projections and add them all up over all the eigenvalues. And that gives you a new density matrix. And that's the density matrix. In general, of course, a mixed state now represents the result of doing this measurement operation. So what would be the simplest set version of this? Well, we got two partitions here. We got pi, we started with. We're doing a measurement on the rho of pi, and we're doing the measurement, in this case, using another partition representing a numerical attribute. So what would be the more mixed state that you would get by this sort of applying this operation to the rho pi here? And so this is how it would work. You've got rho pi here. Your projections are down to your F inverse eigenspaces. Those are the eigenspaces of sigma, as it were. And you add them up over all the elements in the image of the function. And that gives you rho hat. And rho hat is just the join. It's just the density matrix of the join. So that says measurement is just the join operation. When you're doing it classically, and then of course you do the quantum version, so it's like the quantum version of the join operation. And now what we should point out here is, of course, both, we had the same U here. This was defined on U and pi was a partition on U. So we could form this join. The join isn't even defined if they're not defined on the same set. When they are defined on the same set, then the result of the Luther's mixture operation here is just the density matrix of the join. So that's a theorem. I'm not going into proofs here. So the dit set of the join is actually, and this is just a fact in the beginning about partitions, it's just the union of the two dit sets. So the join operation is going to add more distinctions because you're adding distinctions of sigma onto the distinctions of pi, and thus increase the logical entropy. So you're moving up to a more distinct state. Now, let's be even more precise. Remember that we said that the off-diagonal elements that are non-zero in the density matrix represent the coherences. But when you take a join, you're cutting apart some of those things that were in the same block of pi because they're in different blocks of sigma. So those elements will be separated into two different blocks of the join. So we should be able to take the non-zero off-diagonal elements of rho of pi, which represent those coherences, and then look at what happens when you go to you do the Luther's mixture operation on it. And it turns out that the increase in logical entropy takes place here is just the sum of the squares that got zero. So it's just the sum of the probabilities, the new distinctions that were created. In other words, the coherences that were decohered, that were made distinct by bringing in sigma into the join. And that's true. So that says that the logical entropy not only connects directly to the entries in the change in entries in the density matrix and the sum of the decoherences that were created in the measurement operation gives you the increase in logical entropy. So you have the difference between the logical entropy after the operation and before is just as we saw, since after is just the join, it's this logical entropy minus the original logical entropy of pi. And that's what's called the conditional logical entropy of the join. In this case, the conditional means you take away the information in pi. So you're taking what is the additional information in the join that wasn't there in pi in the beginning. Or this is another way to look at it, is what's the additional information in sigma that wasn't there in pi. And that's just the product of all these elements that are in the dit set of sigma that are not in pi. And those are remember that those products are going to be the squares of the elements that got zeroed. Because remember what remember what the elements are when we multiply by the probability here. You just get the square root of these two. So when you square it, you just get the product of pj, pk, and that's what here we're just adding up, which are distinctions of sigma not in pi. So that's exactly what's happening in partition terms. What happens in quantum measurement is that you make these distinctions that weren't there before in the original state, psi in this case, and they all carry over. So I'm not giving the proofs. In the quantum case, they all carry over just with complex numbers involved in vector spaces and all that. So this is sort of the simple version of it at the set level, and everything just lifts right up to the vector space version.
1, 5, 8, 9, 2, 4, 8, 4.
Tom, okay. So that's the treatment of measurement in quantum mechanics, projective measurement, saying that it all boils down to partition math once you re-express it properly in vector space terms. Okay, so let's take some other parts, not just measurement, other parts of quantum mechanics. And one thing that is always said, well, this is so different from classical physics, is that the observables might not commute. That this doesn't happen in classical physics, because classical physics is by definition definite all the way down. So you can get an arbitrarily precise measurement of position, arbitrarily precise measurement of momentum of a particle, and which you cannot do in quantum mechanics. So we want to take this characteristic feature of quantum mechanics, that non-commuting observables, and say, what does this say about partitions? How do we explain that in terms of partitions? It looks like it has nothing to do with partitions. You're talking about operators that are non-commuting. So, okay, here's how we go. So let's take two observables, two self-adjoint operators on our vector space, and each one defines a direct sum decomposition. So let the VIs be the direct sum decomposition of F, and the WJs for the operator G. And as we saw before, what's really relevant to understand measurement is the join operation, the partition join. So here we have two DSDs, two vector space partitions, as it were, and let's take their join. So here's the obvious way to take their join. You take the non-zero subspaces, now not subsets, subspaces that between the things. So for all the different subspaces in one direct sum, they don't intersect each other. I mean, their intersection is always the zero space, but the ones from the different direct sum decompositions can intersect. So we get this. And since the elements in each of the VIs are the eigenvectors of F, and in WJ is the eigenvectors of G, so what's in both are, by definition, the simultaneous eigenvectors. They're the vectors that are both eigenvectors for F and G. So that's interesting. But when we take the join of two partitions on the same set, we always get another partition on the same set. But that may not be true here. When you take these intersections of the subspaces all together, they may not span the whole space. But it is what is spanned by these intersections are they're all simultaneous eigenvectors. So let SE here be the subspace spanned by these non-zero intersections. Okay, so this could be all of E, but it might not be all of E, unlike the set case. So what is the new information that comes out from this, not necessarily the join operation, not necessarily giving us a direct sum decomposition of the whole space? Okay, so that's all defined using partition-like concepts. Now we go back to our operators, and you have the usual treatment. It's the commutator of F times G minus G times F, which is a linear operator on the space. And as any linear operator, it has a kernel. So the kernel would be the set of all vectors where the commutator applies to F equals 0. And then you get a fundamental theorem that exactly the space of simultaneous eigenvectors is just the kernel of the commutator. So now we have connected the commutator, which looked like it has nothing to do with partitions, to the join-like operation on the two vector space partitions, the two direct sum decompositions. And we're saying the result of that is the kernel of the commutator. So it's all directly connects up. And since we know now it need not be the whole space V, we can do a classification. So they commute if it is all of V, they don't commute if it isn't all of V, and they are conjugate if it's the zero space. That means they're totally different. They have no simultaneous eigenvectors. Zero doesn't count. Then it means they're conjugate. So we saw that commuting observables, or commuting direct sum decomposition, it's a vector space version of two numerical attributes on the same set. And that makes them compatible or commuting. So if we have some terminology here for partitions and numerical attributes, we say two numerical attributes on the same set are compatible, but if they otherwise they're not. And if you want to go back to some of the treatments of these questions in the literature, I particularly recommend the treatment by Hermann Weyl in his book on the natural philosophy of whatever it is, science. And he has an appendix on quantum mechanics, and it basically just develops a lot of this framework. So what he calls a direct sum decomposition is a grading, like a sieve. You've got different holes you can go through in a sieve or a grading. And if you're going to combine two gratings, in other words, two DSDs, that presupposes commutability. So that case there. Otherwise, you can't combine them. The join technically isn't defined. It gives you you shouldn't use the word join. You could call it a proto-join or something if they don't commute it, because then it doesn't give you the whole space. Okay, so here we have, again, our connection: set partition, direct sum decomposition, partitions on two different sets of the same cardinality, but different sets. That's like direct sum decompositions on V, where the this SE here should be in kilographic. It's the subspace of spanned by the simultaneous eigenvectors. This isn't the whole space. But if they're partitions on the same U, that's like commuting, where the space of simultaneous eigenvectors is the whole space. And the join in the commuting compatible case is a partition. And here the join is a DSD if they commute. So here we have, on this side, we have a complete set of compatible attributes, different numerical attributes on the same set, that when you take the join, in other words, you keep intersecting their blocks, then eventually you get a complete set. In other words, the blocks are all singletons. That corresponds to Dirac's notion of a complete set of commuting operators, where you all the subspaces in the end are, what is the subspace version of cardinality 1, a singleton? It's dimension 1, and where all the subspaces are dimension 1. So that analogy completely holds here between the two cases. So we have the partition version then to treat the whole difference between commuting operators and non-commuting operators in terms of the join lock operation on the direct sum decompositions defined by the two operators. Okay, let's take another bit of quantum mechanics and see how it can be explained using this partition concepts. So we have the Dirac notion, or no, we have our set notion of compatible numerical attributes on the same set are said to be complete if their join is the discrete partition, where each block is of cardinality 1. Then each element in U could be characterized by a set of values of the attributes. So if you just take the different attributes of this complete set, that each element of U will have a specific unique set of values of these, F and G and H and all the different numerical attributes in your complete set. And exactly the same thing holds for Dirac's notion in the quantum case. Set of commuting observables rather than attributes is said to be complete, Cisco, if the join of their DSDs is the DSD where all the eigenspaces are of dimension 1 instead of being of cardinality 1 up here. Then each of the simultaneous eigenvectors is uniquely characterized by its set of eigenvalues on this set of observables. So that's all standard quantum mechanics, and you see it's exactly the set version brought up to vector space version. Now, and you know here that there is this whole weird thing that happens in quantum mechanics where the particles are said to be indistinguishable. And classically, the classical view is that reality is definite all the way down. So if reality is definite all the way down, that means you could have like two classical particles, and you could distinguish them by, painting one blue and the other red or something like that, making a scratch on one and not on the other, and so forth. So that means that the classical notion of distinguishability of particles treats them as if they're, when you had these complete set of attributes, that they're always more refinable. That if they're not yet distinguished, then you add a new attribute like having different colors and paint them different colors, and now you can distinguish them because reality is definite all the way down. So your partitions can always be refinable, more refined by going down deeper into finding new attributes or new partitions to join, to separate things out, to differentiate things. So that's the classical notion of distinguishability, or definite all the way down. And here is quantum mechanics. In quantum mechanics, however, identical particles are truly indistinguishable because we cannot specify more than a complete set of commuting observables for each particle. In particular, we cannot label a particle by coloring it blue, red, or something else. So just the fact that a particle in quantum mechanics can be defined using a complete set of observables, which you cannot refine anymore. There's no further refinement. That tells you automatically that we're talking about objective indistinguishability. We're not talking about definite all the way down. We're talking about you get down to a certain level and distinguishability stops. You have objective indistinguishability then. And so this quantum indistinguishability immediately points to objective indefiniteness as opposed to definiteness all the way down. So we can't just keep on adding more observables to differentiate these things, that they're defined by their complete set of commuting observables, and that's it. So I'm not going into the whole mathematical difference between classical particles described by Maxwell-Boltzmann statistics and the quantum particles described by Bose-Einstein or Fermi-Dirac, because we don't even need to go that far. Just the fact that you can't differentiate anymore the quantum particle, unlike the classical particle, where you just keep on differentiating, and somehow it keeps on getting more and more refined, and like different scratches or different colors on the particles, which you can do classically, you can't do quantum. So that right there tells you immediately that the whole phenomenon of quantum indistinguishability points to objective indefiniteness. You can only go down so far, and from then on, you cannot distinguish things anymore. So that treats that part of quantum mechanics. Now let's go to the different notions of von Neumann said that we have two different types of processes. So for example, the time-dependent Schrodinger equation. Well, what could look further from partition mathematics than the Schrodinger equation? So that, this is a real challenge to my thesis here. How do you get out the Schrodinger equation from partitions and the vector space versions? Doesn't seem to be any connection in partition mathematics. So von Neumann said there are two types of processes. One, type 1, which you call the measurements, which we've seen are processes that make distinctions. In type 2, the evolution of an isolated system, which is described by the time-dependent Schrodinger equation. So how can we get a grip on this using our partitional concepts? So since type 1 processes create distinctions, the natural characterization of type 2, not obeying the Schrodinger equation, but one that doesn't create distinctions. That would be, so these create distinctions, these don't. Very simple. And so is that true? Is that true? And so let's see. Well, how do you tell whether two quantum states are distinct or not? And the correct way to do that is that two quantum states are indistinct or distinct is given by their inner product, their overlap. Remember, the inner product is called the overlap between the two states. So if you can think of the inner product, the two states, as being the degree of indistinctness. So if their inner product is 0, that means you have no indistinctness. So it means they're fully distinct. And inner product of 0 means orthogonal. So that means that they're fully distinct, as opposed to having some type of overlap. And when they fully overlap in the normalized states, then of course the inner product is 1. So then they're fully indistinct. They are the same. So then I just say this. So the inner product measures the degree of indistinctness or overlap between the column states. And I just said that the natural characterization, from my point of view, and I'm arguing, is that type 2 should be the type of process that doesn't make distinctions. So since distinctness of quantum states are defined by their inner product, that means the natural definition of type 2 is evolution of states that don't change the inner product. They keep the states with the same degree of indistinctness. And so the natural characterization of processes that don't change distinctness or indistinctness would be processes that preserve the inner product. And those are called unitary transformations. And those are exactly the type 2 processes. So we have the type 2 processes characterized. And then you say, well, what happened to the Schrodinger equation? And that is given to you by Stone's theorem. So the connection between unitary transformations and solutions to the Schrodinger equation is Stone's theorem, and this is a statement of Stone's theorem. One-to-one correspondence between strongly continuous one-parameter unitary groups and self-adjoint operators Hamiltonian on the Hilbert space, such that this unitary operator has this form, and that's the form of the solutions to the Schrodinger equation. So the Schrodinger equation comes in via the Stone theorem that reformulates unitarity in terms of solutions to the Schrodinger equation. And that's the connection. So we have given then the partitional characterization of this von Neumann distinction, processes that make distinctions called measurements, processes that don't make distinctions called the evolution of an isolated system, or in other words, unitary transformations. Okay, so we're nearing the end here, and I'm now covered all sort of the main parts of quantum mechanics, and so I want to now make some more intuitive remarks. And the result of this rethinking of quantum mechanics is that the real problem here, which I call the scourge of quantum mechanics, is this whole idea that they're waves. So the wave interpretation of quantum mechanics is the scourge of quantum mechanics. And here's what I mean, that people think of waves in terms of superimposing two definite waves to get another definite wave, definite in italics. So here's two waves superimposed where they're totally out of phase, give you a constant, or where they're in phase, they give you, double amplitude here. So here's two definite waves, and here's a definite wave, two definite waves, here's a definite wave. And it's this interpretation that is the scourge of quantum mechanics. You've got to rethink what a superposition is in order to understand what's going on. And accordingly, there are no physical waves in quantum mechanics. That was Schrodinger's original dream, is there's some kind of wave there. And so we have the mathematics of waves because we have complex numbers. So the wave interpretation arises since we're using complex numbers, and complex numbers are the natural math to describe waves. So the scourge is always going to be there. You're always going to have this wave interpretation, but there's no waves. So it's just because you're using the complex numbers that you always have this wave interpretation there, but it doesn't mean that the superposition of two definite waves is a definite or definite wave, as we always picture it in Fourier analysis or, any kind of. And here's a quote from Dirac that sort of says, such analogies led to the name wave mechanics, and which, thank God, is going out of usage, being sometimes given to quantum mechanics. It's important to remember, however, a superposition occurs in quantum. It's essentially a different nature from any occurring in the classical theory. You know, this is the classical theory version of superposition of two waves, as shown by the fact that the quantum superposition principle demands indeterminacy in the results in order to be capable of a sensible physical interpretation. Thus, the analogies are thus liable to be misleading. So I'm saying, yes, they are misleading. They, in fact, are the scourge. And the whole trick is to interpret the superposition not as going from two definite states to a superposition definite state, as in classical waves, but to a indefinite state that is in between, as it were, the two states that are superposed. And so let me give you an image that will say that. So why are the complex numbers used in the first place? It's not because there's any physical wave being described. It's because we need to go, we have real valued observables, but we need to describe all the eigenvectors of the observables. And that only holds true if you work with the complex numbers, because they are algebraically complete expansion of the reals. So then the real valued observables, in other words, all self-adjoint operators have real valued eigenvalues, will have a full set of eigenvectors, not because you're trying to describe some physical wave. So that's the real little trick here, is that we use the complex numbers because to get all the full set of eigenvectors, you need them there. That's because it's algebraically complete extension, yet it is the natural mathematics for waves, as you see in electrical alternating current theory and so forth. And so that's what creates this scourge of interpreting it by thinking it's like adding together two definite waves to get a definite wave. Whereas you need to switch to the imagery. Superposition means adding together two definite things to get something that's indefinite between the two. And here's an image that gives you that sort of thing. Suppose we start with two isosceles triangles, and you have reflection around the vertical axis there. And the classical scourge interpretation would be it's a superposition. It's a definite state that somehow, it's both B and C here. In fact, you should interpret it as the indefinite state, where you have each side can be made additionally definite by adding a B and a C, but they're not there here. They're not in both B and C. It's like the particle going through the two slits in the double slit experiment, going through both slits at the same time. No, it's in a state that's indefinite, not definitely going through one slit or the other. And here is the proper imagery to use. So the quantum, as opposed to classical interpretation superposition, is the addition of two definite states, in other words, two eigenstates, to get a new state indefinite between the definite states, not the double exposure triangle here, where you have two definite states add up to give you something definite. So that's the scourge of quantum mechanics. Is the wave interpretation, and the classical notion of waves as being added together to give you another definite wave. And yet there's no physical wave. So what the hell's going on? I'm suggesting what's going on is superposition has to have this other interpretation as the indefinite state, because the reality is objectively indefinite, and superposition gives you that. So that's the way to imagine it. And this, for example, we can go back to the imagery of indistinguishable particles. Weil uses tags, artificial tags, Ike and Mike, for two indistinguishable particles. And so you let the ordered pair A, B stand for Mike being in state A, and Ike being in state B. And then you permute the particles here. And so it's analogous to this flipping the axis here. And what it gives you as a result is not Mike is in both A and B and Ike is in both A and B as here. What it gives you is this indefinite state where you cannot say which is which. quantum mechanics, the superposition state symbolized this way, which is like the image of the triangle with the indefinite equal sides, not the sort of double exposure triangle here. I don't know if young people these days know what a double exposure means, because that's something that happened with film cameras. But if you, back in the old days, if the film didn't advance, you got a double exposure. You got two definite pictures superimposed. And that's not what quantum superposition is about. It's not a double exposure. It's a indefinite state in between that could be made more definite to either one of the definite states by making some distinctions. So finally here, winding up, the objective indefinite interpretation is confirmed by showing how the math of QM, which we went over all those major parts of quantum mechanics mathematics, was really the vector space version of the math of partitions, which is the natural math to represent indefiniteness. And so that's where the name of the talk came from. Follow the math leads to the literal or objective indefiniteness interpretation of quantum mechanics. Thank you. Okay. You can
Wow.
stop.